We'll start with Luca Biancofiore from University of L'Aquila.
Okay, yeah, thanks the chair for introduction. Thanks Mark and the committee to inviting me today. So, as the chair said, I'm University of L'Aquila, but I mean until last October I was in Bilkent in Turkey, and since most of his work was done when I was there, I think it's fair to put double affiliation, and I'm still affiliated with them until end of August. So. Anyway, today I will talk about the evolution of volatile liquid films and droplets in the lubrication regime. In particular, somehow summarize, I will try, 3 papers of my group, 2 about liquid films, conducted mainly by my student Omer Mohamed, and the first one is in collaboration with Michael Dalston, one now is in QUT in Brisbane. And the last paper, the second part, is about particle-laden cell droplets, conducted mainly by master student Alike Ramerdem in collaboration with Fabian Denner, that I think you know very well since it's just presented before lunch. Okay, so for liquid films, we said these 2 papers. Application maybe is not, I mean, all of you know why we work in liquid films, most of you work on the topic, but anyway, in particular evaporating liquid films, so evaporator, cooling towers in power plants, structural packing, and so on. There are many applications for just electronics cooling, photovoltaic cell, anyway, many applications in different fields, in different scales, I would say as well. So there is good reason to work on the topic. The goal of all this application, anyway, is to maximize the heat or mass transfer. Okay, so what was shown, I mean, something that a heat transfer in the wave interface can be 100% larger than a flat film. So, I mean, it's important to understand the wave dynamics also in evaporating liquid films to, in particular, understand the different mode of instabilities in the films, how they interact between each other. So at the end, what you want to do is try to enhance the system performance. So in particular, in some of these applications, there is also a shearing gas, okay? And so the first goal was to extend the model by Zhu et al., paper in GFM 91, to include the effect of gas shear. How to model the gas stress? So was shown by King et al. That under long wave expansion, the disruption of the gas flow is quite minimal. And so the important thing is to keep the leading order shear stress, while the leading order normal stress can be somehow neglected. Okay. So at that point we add this quantity tau, okay, but to model in the gas shear stress to model some of the effect of the shearing gas. But now, I mean, let's go back to the main part of the topic of today, that is the evaporation. So which evaporation model to choose? So there are 2 big families. One is somehow the evaporation regime, the transfer rate limited regime, in which the vapor diffusion is not present, okay? And so the evaporation rate is only governed by thermodynamic equilibrium at the interface, okay? So in this regime, the evaporative flux that I represent with J's there at the trough is larger than the evaporative flux at the crest, since it's depending basically on the position, how much are far from the heating wall, okay? So these are many work on this. Now I cite Burelbach, Zhu et al., the review of Ron et al. Anyway, but there are many work on this evaporation regime. The second big family somehow is diffusion limited evaporation. In this regime, we assume there is a gas layer above the interface that is saturated with the vapor. Okay, and so at the end, the evaporation rate is governed only by the vapor diffusion in the surrounding gas. Okay, so in this model, actually, we have the opposite behavior. So the evaporation rate is larger at the crest than the trough. Okay, so I mean now Sai Sultan et al. Actually their model is a bit more comprehensive, but anyway, just an idea. And also, I mean, the famous paper of droplets, actually, Deegan et al., also cited yesterday in the talk of Madeleine Moore. Okay. Anyway, so with this in mind, let's work our equation. These are the liquid film sheared by a gas. I mean, we have this additional term. No, sorry. Let's first visit all the equation with the governing equation. I mean, the usual sum of stuff, Navier-Stokes, momentum equation, and the equation interface. And with the long wave expansion, we can reach this Benny-like equation, what is similar to Zhu et al., but we add the shearing gas, what is highlighted in the kind of lila, I guess. Anyway. So the parameters that we want to highlight, and there are many in this work obviously, but anyway, it's about the mass loss effects, thermocapillary effects, so we call Marangoni, but we don't have solutocapillarity, just thermocapillarity, and vapor recoil, okay? So, I mean, we do linear stability analysis, so we normal modes, so H0 is the base state height, and as you notice, it depends on time, but we can apply a frozen interface assumption that was introduced first, I mean, as far as I know, by Burbeck et al. In '88. Okay, and we reach this dispersion relationship, now it's really dispersion relationship, in which we are added, I mean, the Zhu et al. Basically with add this term of the shearing gas. We can do temporal analysis, so stable versus stable, or spatio-temporal analysis in which we can understand if the flow is absolutely unstable or convective unstable. So anyway, let's look at the term linear stability temporal first, okay? And so we have two main instability modes. One, let's call just thermal mode, okay? In which we are, now we're associating Marangoni plus vapor recoil, and this acting as more Reynolds, okay? While the second mode is the classical mode, H mode, we call hydrodynamic instability, but is considered inertial effects, is due to inertia, and is acting at large Reynolds. So we define the dry out time, so how much time somehow the film needs to dry out completely, and we normalize the time with this TF is T over TD, basically. So first of all, let's look at the shearing gas. The effect of tau is much stronger on the H mode, okay? So we can see, I mean, these 3 tau. While for the thermal mode, the effect of tau is minimal. So the other effect that was interesting for us was the thinning of the film, okay? So obviously, we see that for the H mode, the thinning of the film is suppressing it. Okay, the film starts to be thinner and thinner, so it's more viscous. Viscous forces are stronger, and so eventually we kill the H mode. The thermal mode actually is enhanced. That was an interesting point. So, I mean, looking at that, we say, okay, let's focus on thermal mode. I mean, in the paper, there are many more results, but anyway, let's focus on thermal mode. Somehow, let's forget what is happening in H mode, and study the spatio-temporal stability. So now we are plotting somehow the full impulse response in the plane sigma, the temporal growth rate v, the group velocity, and the important point is this green circle, is small, I don't know if you can see. And so if it's positive, it's absolute, if it's negative, it's convective. And what we can see, first of all, that the evaporation of the film strengthens thermal mode, okay? It again is weakening gas effect. So also a shearing gas, when the film is thinning, is not such a big thing, okay? And anyway, what we can see, I mean, for 1 tau, but I say it's not changing quality, it's not changing anything. The absolute region is growing and growing with the thinning of the film. So we expand this. So it looks like that the instability spreads faster due to new modes, but we have higher group velocity. So that's what I found interesting. So we also study nonlinear evolution now. So this is a movie somehow. Oops, maybe I should agree. You can see now, basically, initially, the stability skill somehow is dampened initially. After it starts, maybe you can see also for this spatio-temporal evolution, first it's going down, after it starts to grow, but it's advected away. So a clear convective instability, okay, in this part. Eventually, when the film is thinning, it starts to be absolute. The wave front is stable, is stationary somehow. And so it's a clear absolute instability. It can be seen also from the wave front somehow. So the real edge eventually starts to be flattish. Okay. Okay, that was an interesting result. But, I mean, like we said, this gas, shearing gas was not such a big thing for thermal modes. I mean, the paper is also about each model things. But if the shearing gas, in some other application, there is not a shearing gas, right? So, so if there is not a shearing gas, we cannot assume that there is no desaturate layer. So there's nothing that is advecting the vapor away, this gas layer, this saturate gas away. And so we should somehow change the evaporation regime. So in particular now, let's start from the model of Sultan et al. 2005, but we modify it for accounting also mass loss where they somehow neglected. So in this model, what we say that the normal vapor flux across the interface should be continuous. So the normal vapor flux departing the interface, that is regulated by the Hertz-Kruger equation, somehow should be equal to the normal vapor flux that is diffusing into the ambient phase. Okay, and this is regulated by Fick's law. So with some calculation, putting these things equal, eventually you find a boundary condition interface, what you can see here somehow, in which you have two additional parameters. One is the kinetic Prege number, okay, but it's kinetic time or diffusion time, and the second one is chi, but is somehow determined the density fluctuation. So in particular, what we notice that the ratio of these two, what we call gamma somehow, determines the evaporation regime. If gamma is smaller than 1, the kinetic effects are stronger, okay? And eventually, when it's going to 0, it's dominating, and so we have the transfer rate limited regime. When gamma is larger than 1, diffusion effects are stronger, and when we are going to infinite, we obtain somehow the purely diffusion limited regime. So anyway, now, we should not solve only for the liquid, we should solve for the gas. In particular, we need to solve for the density of the vapor in the gas. So we should solve the Laplace equation. At the top boundary, we use a constant of flux to maintain the quasi-static diffusion as the film fins, okay? At the end interface, okay, we just talk about this kinetic diffusion balance, or we need to solve obviously periodic boundary condition along X, and we can solve for rho v, and J, the evaporative flux, is connected to rho v through the Fick law. And so this somehow is a graphical picture of what we have, and we should couple this with our governing equation that somehow we studied already earlier, but now this time J is given by this law that we found here to the gas. Okay, nice. And somehow just to highlight, okay, I just already said, but we don't have any shearing gas now. So from again, we can obtain again through the long wave expansion a Benny-like equation, and we can obtain from the linear stability analysis again the dispersion relationship, in which we have three terms connected to the parameter that you want to analyze. So the mass loss instability connected to E bar, so is accounting for mass loss, Marangoni instability, but is talking about thermocapillarity, and the vapor recall instability. But the Marangoni instability, thermocapillarity, is divided in two terms now. One is the first one, is taking care, is regulated by the surface tension variation to conduction, this term here. And the other one is the variation of to latent heat cooling. So time variation due to latent heat cooling. So now, let's look at this term. Now, we can see that all the three, they are changing obviously with gamma. And in particular, when gamma is smaller than 1, when kinetic effects are stronger, I remind you, mass loss instability and vapor recall instability destabilize the film, while the opposite occurs when gamma is larger than 1. For the latent heat cooling Marangoni instability part, somehow with a different effect. So Marangoni is stabilizing when gamma is smaller than 1, and destabilizing when is larger than 1. So now let's obtain somehow, let's work on the special limits, special cases. The first one, we already said, when gamma is going to 0, we have a transfer rate limit evaporation, but somehow we already analyzed. Now we don't have the gas, so why do that? The two Marangoni terms, they combine in only one. And we obtain exact expression in Zhu et al. So for the diffusion limited evaporation, so when gamma is going to infinite, the two Marangoni terms, they remain distinct, okay? And they are also in the different order than the one number k. And so we obtain another expression that we reported here. So now let's try to find an explanation to that. The thing is this. As I say, the conduct heating, that is somehow creating one of the parts of the Marangoni stability, is due to fin-thick differences, okay? While the second part, due to latent cooling, is due to evaporation rate difference. In the transfer rate limit evaporation, the evaporating mass flux, so this evaporation rate somehow, depend as well on the film thickness. So both terms will depend on the film thickness. For that reason, then they will combine in one unique term. Under the diffusion limit evaporation, when so gamma is going to infinite, the film thickness is not important to determine the evaporative mass flux, is the interface curvature and the gradients of vapor density. And so at that point, obviously there are two different terms depending on two different, differently from the wave number. The last special case is when gamma is equal to 1. So we call balanced flux evaporation. In this case, the free stability connected to the evaporation, all of them eliminated. So we have a flow, film, but a volatile film, let's say, that is completely devoid of evaporative instability. Okay? How is this possible? I mean, this is possible. We can also do a numerical simulation of the Benny-like equation somehow we found. When gamma is equal to 1, kinetic effects are exactly equal to diffusion effects. So the film is going down, and evaporative flux at the crest and the trough are exactly the same. For this reason, we don't have any stability connected to evaporation. So now let's look at this term, somehow a bit new term, since it's something that in Sultan tunnel was not present. Okay, this latent heat cooling that somehow is creating some self-tension variation anyway. So another Marangoni effect, another part of Marangoni effect. In this case, you see when gamma is smaller than 1, is diminishing the instability. So a stabilizing effect, we already said. When it's larger than 1, is amplifying. Okay, since that term will be positive. Okay, in the other term, in the other part will be negative. And so clearly, I mean, the growth rate will grow, okay, significantly with gamma, as you can see in the figure there. So now, but okay, we choose these parameters in the previous figure for the vapor recoil and the E-bar, but are quite moderate small anyway. What does it happen when we increase it? We see that here I represent the growth rate in gamma k. We see that for large gamma, the vapor recoil in this case is killing the stability. Let's start again. It's killing the stability on the diffusion limited regime, and is amplifying the instability in the transfer rate limited regime. Similar thing is happening for E-bar. Somehow the two effects are quite similar. Okay. So we are killing stability for large gamma, so diffusion limited regime, and we are enhancing the stability for small gamma, so transfer rate limited regime. So no, it's not the last actually. The second last thing I would like to say is about the mass loss instability. This somehow was a bit neglected in the previous work of Sultan et al. Since somehow this term we are not really talking so much. And I mean, we have to also in this term, I mean, let's study the different. Add some weight. But you still listen to me? Try again. Okay. So in the transfer rate limited regime, okay, let's try. When gamma is to 0, this term is becoming independent of the wave number, since we don't have any vapor gradient, okay? And so the evaporation rate is completely doesn't depend on the shape, okay? Depends just on the position from the wall. While in the second term in the second regime, the diffusion limited regime, is depending on the wave number. This due to the effect that is depending on the shape. Okay, since it's depending on the curvature, the interface. Okay, curvature of the interface. And so in this regime, obviously a different K means a different shape, and so a different evaporation rate, so a different mass of instability. One thing is important I would like to notice, when Burerbach et al., Zhu et al., this term was somehow a bit neglected, say it's algebraic. Okay, and it's true. When in transfer limited, it's algebraic. But in diffusion limited, no. Obviously, it's dependent on the number, it starts to be a pure exponential instability, usual. And this can be seen also from this numerical simulation we have done when gamma is smaller than 1 and gamma larger than 1. When gamma is smaller than 1, we see that a pure mass loss instability, vapor recoil is 0, Marangoni is 0, is still destabilizing the flow, while this is here. While for gamma larger than 1 is stabilizing. This is interesting. It's a vapor recoil instability. What does it mean? It means that we have an instability to the effect that we have a density gradient between liquid and gas. Okay, liquid and vapor. Okay, sorry, no gas, vapor. But in a case, I mean, very theoretical, in which the density, we don't have a gap in density between liquid and vapor, we still have an instability in some cases due to the fact just our molecules are departing from interface. Okay? So now the last thing about the film, at least, I mean, somehow the effect of the film thinning, what we found interesting before. Let's see what is happening in the diffusion limited regime. We have seen for the transfer rate limited regime what the effect of the film thinning is destabilizing. This occurs also in the diffusion limited regime just when the evaporative effects are weak. See the first line, the first figure. When the effects are strong, conversely, we have a complete destabilization. In between, moderate, we have somehow an optimal value for destabilization. And this can be seen also in the spatio-temporal part. Since in the transfer rate limited regime, we have seen a shifting towards the absolute stability. Same thing for the diffusion limited regime, only when the evaporation effects are weak. When they're strong, we have a shifting towards convective instability. And when are moderate, we have again an optimal value. So anyway, in conclusion, we have seen when kinetic diffusion effects are balanced, we can also create a volatile film complete devoid of evaporative instability, not only evaporative instability, is a mistake. So all the evaporative instability. A pure mass loss instability is observed for gamma smaller than 1, but it starts to it's not dependent on the wave number anymore when we are going in transfer rate limited regime. The Marangoni instability is two terms in general, in particular under diffusion limited regime, and only one single term in transfer rate limited regime. We notice that the evaporation regime is modified significantly the effect of film thickness, and this to have a rich interaction between Marangoni evaporation effects. Future work analyzing the stability experiment, this will be really a strong help. Also DNS, actually we have a chat with Mirko in this workshop, so it's something useful for sure. And for a PV cell application, we are trying to include radiation in collaboration with Professor Christian Riverkey. So I still have 5 minutes, I hope, right? Okay. So I would like to last topic for today. I mean, the particle latest SL drop, also in collaboration with Fabio. I would like to present briefly at least. So again, application where maybe it's not a good public to convince you why we should work and evaporate SL drop, so maybe I skip. But since all of you know what is important. So by all of this application, what is interesting to understand how the concentration and the deposition of the particles are evolving. Okay. So we have two regimes, I mean regime everywhere here in this talk. Pin regime, in which the radius of the droplet does not change, and dependent regime, in which we have a moving contact line. So, so what we want to do somehow? We want, first of all, develop an algorithm for both pinned and moving contact line. We're using the slip velocity, somehow slip length that Stefan Zaleski talked today. There is a lacking literature in this topic with lubrication theory, since in general people use, also brilliant, it's not time against, a precursor film, okay? But it's useful for some application, for other maybe less, okay? So you want to include, so the temporal evolution of the droplet interface, the contact line dynamics, the entire contact line dynamics, particle dispersion, deposition. So at the end, we want to understand how different parameters play with the final stain left by the droplet. I mean, the famous coffee ring effect, again, Digo and et al., but is always cited. So now, from a definition, quickly 2D, Cartesian, we have a passive vapor, so the droplet is, the wall somehow is a uniform temperature. So first of all, unfortunately, the first step was to use a transfer rate limited regime, since we talk a lot about diffusion limited. Look a step back, but obviously it's more complex, so we initially always start with something a bit simpler. This is the equation for the concentration of the particles. We have particle deposition here, as in the boundary condition, and the contact line dynamics. But somehow we copy-paste what we use Anderson and Davis in a paper on 95. Okay? So, assumption, lubrication theory. So, one-sided model. So, the quantity of the vapor are much less important than the quantity in the liquid. Rapid vertical diffusion was introduced by Carapezza et al. In 2011. Okay, we don't know completely introduced, but sure we use somehow their construction, in which somehow what you are saying that the concentration does not depend on y, just on x. Okay, the positive particle will not return to dispersal phase, and the droplet is dilute, so we don't influence the flow. The only thing is changing actually is the viscosity depends on the concentration. Okay, so we non-dimensionalize now with many parameters. I will not talk about it. I just highlight this theta, but somehow is related to the spreading of the droplet. Since it's what I'm showing today, what does it change? So this obtained this low order evolution equation, in which I've done Kohler number, evaporation, all the package number, all the package will not talk today, so for time limit. Numeric was a bit painful, I mean, like Fabian knows. Anyway, just briefly, what we have done. First of all, we define the deposit mass in each node, and what we are showing also is the accumulated particle density. So in each node, how much mass is in the delta X, somewhere in the grid. Since we also use a non-uniform grid, so I mean, this also complicated a bit, but was the only solution to reach this point. Another important parameter is theta lim, is the contact angle, limited contact angle. Since we say that below this contact angle, the droplets start to move, to recede. Okay? This actually we choose, this was something shown by Wu and Larson, in the range inverse experiment was between 2 and 4 degrees. But anyway, we talk later about that. We need to correct H for every time step to conserve the fluid mass. Correction of the concentration as well, to have all the same particle, total particle mass, deposited and dispersed, okay? And we stop the simulation when we reach 98% of the total initial mass particle. So, we choose a set of parameters, theta limit is also chosen, 2 degrees is the non-dimensional value. So these are the droplets somehow, the evolution of the droplet, the thing is, so it's basically, eventually is the pinning, okay? The concentration, how does it behave? There is a clear peak occurring at the boundary. Eventually, this clear peak is also moving with the droplet, and also accumulation of particles. But mainly in this graph, so in this simulation, we have a clear Coffey-Ring effect since we have the highest peak at the boundary. So anyway, what does it happen when we change parameter? I mean, we changed so many parameters in the paper. If you want, please read. It's just published last month in Langue. But now I show just a couple of things that are really devoted to our model, okay? So first of all, the effect they say the droplet spreading. So with the contact line motion, there are two terms. One connected to evaporation, that is the recession of the droplet, and one the spreading. So obviously spreading actually is not depending just on theta, it's depending on the package in this f theta. But obviously it was a bit complex, also maybe redundant to modify all the parameters. So we just play with theta, also the values are not so physical, but we can reach modifying the others. Okay, so what we see that initially the spreading is favored. I mean, makes sense. We increase eta, increase the spreading, but eventually by increasing eta, we start to have lower contact angle, and as you see here, a lower contact angle is increasing the recession as well, and so eventually recession is also winning at the end somehow. It's stronger than for large eta, so that was a bit counterintuitive, but it was explained. At the end, what we see that a lower deposition close to the center, since at the end, being slower recession in general, we can somehow have more time to deposit in between. Last result, so the last of the last, I promise. So the effect of limiting contact angle. So the pinning now is obviously occurring earlier for large theta lim, okay? And we're increasing theta. So theta is occurring is always larger, okay? And so increasing theta, if you go back to the previous, we are slowing down the recession, okay? So at a point we have a peak of concentration that is decreasing with larger theta lim, and this at the end is resulting in a more particle close to the center, and so somehow we are killing somehow the Coffey-Ring effect. So conclusion. So what we have done, we combined moving a pinning contact regime in a unique algorithm, including also particle dispersion and deposition, using the slip velocity and not the precursor film like most of the, all, as far as I know, all the paper in the region. So we observe a stronger particle deposition at the center by increasing the limited contact line angle, a clear Coffey-Ring effect by enhancing the spreading. We know this results from Marangoni, Dan Kohler, Peclet, all these packages written in the paper. What we will do next? Experiments. Actually, this project was in collaboration with experimentalists in Turkey, where I was before, but we didn't find students until last few months ago, so we don't have results yet. Model particle-to-particle interaction, flocculation, clustering, and so on. And obviously, after all the work I've done in phonographic frames with evaporation, we would like also to implement a more accurate evaporation regime, but this will be also quite strong novelty from the literature. Thank the students, thank the collaborator, Fabio is here, so I can thank him personally. I would like to thank also TÜBİTAK, as a national research agency in Turkey, for free project between droplets and films. And also we are having a student, so between L'Aquila and Vienna, if some of your students is interested, please tell them to contact me. I finish.
Thank you very much.
Thank you.
Are there any questions?
There's a lot of debate in the literature about when you should use transfer rate limited versus diffusion limited. Do you think this gamma parameter is sort of the defining tip over?
Yeah, I mean, yes, with gamma somehow we can divide both. We would like to interpret, it's not the first introduced, was Sultan et al. We did for the film. I think for the droplets, I think you work a lot on droplets, it's also a stronger debate. And I think with these, honestly, I'm not aware of some user exactly Sultan model for droplets, maybe there are. But I think that will be something, I mean, at least you can play with some additional parameter you can play with, okay? You can tune with the experiments accordingly.
Thank you. You mentioned in your perspective some experiments. Do you have any,
Which part? Droplets
the
or film?
first part.
The first part, unfortunately,
do you have any, is there any experiments that somehow witness of,
No, okay, I will be honest.
You
These,
observe or your prediction
for instance, the vapor recall instability from the 70s, we are talking about it. As far as I know, it's something of Palmer, I think. But honestly, I don't, I mean, it's 75, so 76, so we're talking about 50 years ago. So it would be nice to have something more recent. Honestly, since this colleague that she wants to do experiment on droplets, she likes to do experiment on vapor. You see, let's start to have a look at it, but I think much more complex on the droplets if you are already in mind. So I don't know, we have some group doing that, I think, in the US, but are large scales. Large scale, I don't think you can see this stability are really at the macro scales. So it will be very nice. I mean, not experimentalist. I think it will be very hard, but obviously, the challenge is there.
Thank you.
Anybody else? So let's sing the speaker again.